Okay, so here we are in the second part of the transistors lab. I have gone to a different orientation for the video. Hopefully it looks a little nicer on YouTube. I was, upon further research and just looking at it, it seems like the vertical orientation for videos on YouTube kind of is terrible, so, or less good. So, in any case, these are the circuits we're going to concern ourselves with today. This one over here actually is the one I've implemented over on the circuit board. We'll get there in just a second. But in your lab procedure, this is the second portion of the lab where now that we've found the so-called saturating current for these bipolar junction transistors, BJTs in short, okay, which for us was like maybe 4.5 volts from our data, if you remember that part. If you haven't done the first part of the lab or looked at that video, you definitely should before you get into this one. Anyway, what we've done, and as the procedure tells us to do, we've put another transistor in series with the first. You see that the first part of the circuit with a 100 ohm resistor, ballast resistor in series with an LED, that's all the same. And the rest of the circuit is the same. So we're just highlighting the relevant difference here with this extra series transistor. And you'll notice that if we zoom in here a little bit, that now we've got two separate input voltages. The first input voltage is going to be controlling the first valve, the first transistor. And the second input voltage is going to be controlling the second transistor. And you can see, knowing what you know about circuits and looking at this circuit, that unless both of these valves are open, right, then no current is going to flow from the supply voltage high side through the ballast resistor, through the LED, and down to ground. Because if one is open, that's great and all, but if the other one is closed, because they're in series, and things in series must experience the same current. If this one is closed, so we're getting a ton of resistance there, basically like an open circuit, then you're going to get no current flowing through the LED, and we should expect that no light flows. Okay? Now, to review, come up here, to review our saturating current, which remember this voltage data can be converted to currents, and you did that, or will do that for the first part of the lab, okay? We saw that if we put in on the control side 0 volts, 0.5 volts, 1 volt, 1.5, all the way up like that, then we got steady increases in the base voltage, which is a proxy for the base current. So as that goes up, the base current, the control current goes up. And we can see that making steady steps upwards, right along with the current actually flowing through that ballast resistor and thus through the LED itself. So that goes up and up and up and up and up, and then of course we come up here to the top, and you'll notice that it flattens out right around at 4 volts. So you can see sort of a sign that it's not sort of flattening out, it's saturating, it's going to its highest point, whereas this one keeps on steadily going up in regular increments. So if we come up here, we definitely have it flattening out right around 4.5, maybe 5 volts. And because in this case we're dealing with two different transistors, nominally all of these main transistors are going to saturate at the same base current. However, that doesn't always happen. There are small changes between two transistors, and so what we're going to do is we're going to pick a point for our control voltage, and thus our base current, that tiny control current that we're using to control whether the valve is open or closed. We're gonna use control currents that are saturated, so valve all the way open for this portion of the lab. At about 5.5 volts, just a little ways into the saturation, so that we make sure that both of the transistors, when we apply 5.5 volts to their inputs, are going to be completely open, meaning that the current flows through them more or less unimpeded. All right. Now, the basic idea of this lab, if we come back over here, is that now we're no longer, sorry, let's pop over here first. We're no longer looking at this regime where, back up just a minute here. We're no longer looking at the regime over here where things are linear, right? We've found this portion where it saturates, okay? So the switch or the valve, however you want to think about it, is either all the way on or all the way off. So all the way off would be, of course, down here, and all the way on, or the valve is open, would be over here in the saturated version, regime, I guess you could say. All right, and so 5.5 volts for us is gonna be right sort of in this regime. Sorry, autofocus is having some trouble. There we go. Okay, so about right around in there, so where it's really flat, and we can be sure that the valve is all the way open. In other words, current is flowing and our light is going to be on. All right? And with that knowledge, knowing sort of how we can open and close circuits, come back over here, we can use this as essentially digital logic. And this is what's done, except at a much greater and grander scale in computer chips. All the computer chips in the world, all that logic where you put a particular input in and you expect a certain input out, and all these calculations that are made in computer chips are all based on and, or, nor, NAND, all these different kinds of logic gates. And we're just going to look at a couple of basic ones. The so-called AND gate, which this is an example, the one we're building today, and the OR gate, which we won't build today, but you're going to be asked about the theory of in the sort of post-lab questions. Okay? So TTL OR gate. So transistor logic, TTL OR gate. So to concentrate on the AND gate, remember what we said about how the current is going to flow if everything's going properly. If we use the saturating base current on this first one, so we open it all the way up, we put our input voltage at 5.5 volts, but we don't put any input voltage onto the second one. We say it's 0. We just hold it there. Well, then this valve will be open, this valve will be closed, and no current will go through. Okay? So that transistor we call a 1 because it's true, it's open, and we call this one a 0 because that one is closed. Okay, so no current's going through it. So in digital logic, that would be a 1 and a 0. And an AND gate, so this whole thing tells us that both of these must be on if you're going to get current through your LED. Okay, so it's not either or that can be on. It's both must be on. Both must be allowing current to flow for the logic gate to say, yep, that's true. That's a 1 instead of a 0. That's an LED on instead of an LED off. Okay, so that's the AND logic. In the OR logic, and you'll think about this in a little more detail in post-lab, like I said, now we've got the two in parallel, you'll notice. Okay, and when you've got them in parallel, either transistor, either valve being open and allowing current to flow turns on the LED. And I think if you think about that, you'll see that that must be true. And so there are more conditions under which this one will allow current to flow through the LED than the AND gate that we're building here today. Okay, so let's have a look at that. Here it is over here. Again, kind of a lot of components. Not too many more than the last time that we looked at this, but a few. Let's take a look. So there is our resistor in series with our LED. And then the LED, let me sort of turn over here on the side, goes into the collector of the first transistor. And you'll see that this blue wire is connected to the middle wire on that transistor. So that's the base connection that comes out here, goes to one of our control voltages on the orange wire. That's control 1, that's input 1 on the diagram. And then that transistor is in series. So let me tip it over here on the side and see if we can get a better look. There we go. Going blind a little bit. Okay. So current comes into the collector of this one. Collector. And if we've turned it on from the base, then current will pass from the collector to the emitter. And that emitter is in series with the collector of the second transistor. So these two transistors are in series. We have a separate control voltage for the base of this one, and then the emitter goes to ground. Okay, so there's the control. Oop, hold on. There we go. So there's the control voltage, second input on the circuit diagram going to the red wire here. Okay. Oh, and I've just noticed something that I haven't put in. So let's put it in now. Okay. You'll note that we have current coming in, going through the LED, going through first transistor, going through second transistor, assuming they're both open. And then where does it go? Uh-oh. All right, we forgot a connection to ground. So, or I did rather. So we'll put this in here. Maybe. Come on. Okay. So this right here. Please. There we go. Excellent. All right, now we should be able to actually turn on and turn off things. Okay. Complete the circuit where we weren't going to be able to before. All right. So now, in terms of what we're looking at, there's the emitter of the second transistor. Current can then flow through the green to ground and back to one of these yellow wires that are all connected to ground. All right. These two connect to the inputs 1 and 2. Right, to the grounds there, and this one goes back to the ground of that fixed 5-volt supply over here on the right. Okay. And as far as what we're doing on the DC source side, that is the supply for the LED, and these two variable voltage power supplies are the ones that are doing input 1 and input 2. All right. Now, with that little bit of nonsense out of the way, okay, you'll notice that I've already got it set up so that the saturating voltage is being applied. That 5.5 volts is being applied to input 1. So that one is telling us that this transistor now, the first one in series, should be open all the way, okay? And open all the way is a 1 in digital logic. So if you're coming over here to your so-called truth table, you got input 1, input 2. So we're in this condition right here where input 1 is a 1, so it's receiving the saturating voltage, which gives you the saturating base current that you need to open up that valve. And the input 2 is at a 0. In other words, it's not receiving that necessary 5.5 volts on the input. And so that's what we see here. I'm not applying any voltage whatsoever on this second one. Okay. Now, if I open up that current and I turn up that saturating voltage to 5.5, you see that our LED is now very happy and glowing. Yay! So there it is. There's both of them at the saturating input voltage, which gives us that little bit of base current, just enough to open up the valves both all the way. Okay? Now you can play around with this. If I were to say take input 1 and remove the input voltage, put it down to 0, so turn it off, right? There we go. So now this one is at 0, right? First input. Second one's still at the saturating input, but there's no current going through the LED because this valve is closed, okay? And that means that no current can complete the circuit. All right. Now, if we turn them both down to 0, well, as you might suspect, if you have both valves closed, then you're sort of making doubly sure, I suppose, that there's no current going through the LED. So the only condition under which you can get current through the LED is when you've got the second input, second valve, second transistor in our circuit up to 5.5, and then as we raise the other one up to the saturating input voltage, there's our nice glowing LED. So, okay, that's what we've got. And that should allow you to fill in the truth table. Remember, ones are current is flowing, or should be able to flow. In other words, valve is open, transistor is allowing current to flow through it. And zeros are closed off, so current can't go through. And that's dependent on whether or not you are applying that saturating voltage to the inputs. So right now we've got a 1 and a 1 for our control voltages, giving us light, which is very exciting. Okay. Now, just in case you were a little bit confused about the connections, let me just step through it real quick right now, and that will finish up the video. Okay. So again, we've got our 5-volt fixed output. So in other words, that 5-volt difference between this green wire and this yellow wire is always the same, okay? And that's directly connected to the ballast resistor, that 100 ohm ballast resistor. That is in series with the LED, okay? And then the LED is in series with both transistors, so the current comes in here, flows from collector to emitter on the first transistor, flows from collector to emitter on the second transistor, goes through the hastily installed connection to ground, the green wire here, and then returns to ground through any one of the yellow wires there, I suppose. Okay. And the base currents, so the control currents that we're putting in with those input voltages, remember those connect to, come here, and get my pointer in frame. Okay, so that first transistor, so input 1 is being controlled by the voltage coming through that first 33 kilo ohm resistor, and thus being controlled by this first input, and that variable voltage supply. And then the second one, again coming over here on the side, right there. That second input comes down through the blue wire, down through the 33 kilo ohm, and connects back to the high side, the red side, the plus, of this second variable voltage supply, okay? Now, we could implement like, I don't know, like a 3 transistor AND gate, right? So all 3 would have to be turned on, in other words, receiving that saturating current, so that they all open up and allow current to go through the LED. We would, of course, need 3 independent variable power supplies. We only got 2, so we'll just stick with the 2 transistor AND gate, but you'll be asked a question or 2 about that kind of thing. And the conclusions you might come to, I think, are pretty obvious once you get the idea. So, there'll be some supplementary materials regarding this portion of the lab posted on Brightspace pretty soon. The report, instructions here at the end of the procedure that is now available on Brightspace, is due on the 17th by noon. Okay, so that's not this coming Friday, but the next one, 17th of April, 2020. All right. Hope this was a little bit of a better experience than last time. If it wasn't, my apologies. And these, still just learning the ropes here. Thanks for viewing.